Welcome back to Neal on Fire. Today, I'm excited to have with me someone who started as a wildfire researcher at NOAA, spent several years in electrical construction and distribution before founding Grid IQ. Welcome, Aren Page.
Thanks for having me, Neil. Appreciate you having me.
Absolutely. So, just a quick note, I'm not paid for this podcast. I'm just trying to help the wildfire community by talking about innovation in wildfire technology. So, let's get into it, Aaron. From what I read in your Rolling Stone article, which I think that's like some serious cool points there anyway. Like, we're talking about wildfire tech and you've got an article in Rolling Stone. Like, that's pretty awesome. But from what I understand in that article, the idea for a Grid IQ came out of the Tubbs fire when you were living in Santa Rosa. So how did your time with NOAA and PG&E and everything else that you'd done in your career lead to inventing Grid IQ?
Yeah, so this is kind of the best origin story that I like to pitch when I describe my business to anybody. But really, I grew up in Santa Rosa and Petaluma. I lived in both places, wild, fire-prone areas. And actually, at the time of the Tubbs fire, I was not living there, but my parents were. So I had the opportunity to come back down to that area and help out for water, help people, evacuate, move, whatever, and then also be there for family. And a lot of my good friends in that area did have their houses burned down. So it really affected me in a way, seeing that, a stable community, a stable city could essentially experience such sort of devastating disaster at the drop of a hat. It wasn't something in my consciousness growing up there thinking that this could be, something that the North Bay would ever experience. And so from that, it really got me inspired to say, if I'm going to spend my life doing something meaningful with my career, why not tackle this problem? Why not try to figure out what I can do to help this situation? So at that time, one of the first steps was working at NOAA or NOAA, National Oceanic and Atmospheric Agency, for those who don't know. And I was really doing burn scar analysis research. So essentially, I was looking at places that were burned by wildfire and understanding the risks that came post burn. Are there landslide issues? Are there debris issues? And this was sort of a new concern based on some events that had happened in Southern California and Northern California. I was like, what are we doing? And through that process, I really started to understand more deeper of, what is wildfire causation? What are the post risks? What are the pre determining factors, et cetera? And during this time, we had, our major utility was also going through the process of understanding how to build better wildfire hardening systems into the grid. And so the grid in California is responsible for a significant amount of the ignitions of these really devastating wildfires. So instead of, going to blame, I said, what's the best way to solve this problem is let's go help them and let's go see if I can have a say in being part of the solution, right? So I went ahead and I got a job at the utility. I worked in multiple different sectors, from substation design, distribution engineering, and then wildfire hardening of the grid. And so to kind of put it into perspective, fires will ignite multiple ways. And sometimes it's vegetation contact on an overhead conductor. So maybe a tree will fall, maybe a branch will fall, and that causes what's called a crossphase, or pretty much connects the grid circuit in a way that shouldn't be connected, causing a spark or an arc, etc. So that's one factor. The other factor is maybe the conductor's just wearing out. There's small arcing. It sparks that the security infrastructure that currently exists can't pick it up. And so that's another causation, which we've seen in the LA fires and the Eaton fire. That is similar to what occurred. And then, then we have just basic aging infrastructure. So ultimately, looking at the grid as our first point of, building robustness into wildfire ignition is where we kind of want to put our eyes and our focus in. So that was really the pathway. I wanted to be part of that solution. Going to the source of it, I think in any problem is a good way to think about, creating solution. And so worked for the utility, left the utility and worked for a consulting firm, engineering consulting firm, doing engineering design, specifically focused around wildfire hardening. And then had the opportunity to do feasibility studies and interconnection projects and things for all of the other Western states, Arizona, Montana, Oregon, et cetera, and of course, California. And then through that process, this idea was still in my head of there's some infrastructure that needs to be built on the grid that we don't currently have, which is why these problems are rising, right? The aging infrastructure combined with sort of a I don't want to say archaic, but older design of protection. And so there's got to be a crossroad here of solution. And so what I really figured is understanding what could go wrong before it goes wrong is critical, right? I think that anytime we can act proactively versus reactively, we have the opportunity to create significant change. Instead of wait for the disaster to happen and then deploy and fix it, it's let's figure out what could go wrong before it does. And so that's where Grid IQ's focus really is understanding the health of our power grid so we can make educated decisions before we experience something like Tubbs Fire or Eden.
Got it. So let's take it from that level down to the level where anybody listening to this can understand exactly what Grid IQ does. So I run into you at a party, like, hey, my name is Aaron. I work at Grid IQ. And I go, oh, what's that? What's your response that anyone listening to this will understand?
10-second elevator pitch I love to say is we're building a nervous system for the power grid, right? You think about most engineering designs that are successful, that last a long time, have some sort of resonance to biomimicry. So biomimicry is anything that parallels something that you find in nature, right? Like the human body. Like no one designed us necessarily, like another human didn't design us, but we have a really intricate system, right? And so part of that is a nervous system. It's a series of electrical pathways essentially that can pinpoint certain things along your body. If you have a pain on your arm, you know exactly where that pain is. And so that's sort of the thinking process behind what we're doing at Grid IQ. If there's a pain point in the exact area being infrastructure that's wearing out, some sort of problem, we can see that pain point and then take care of it before it becomes a bigger health issue, essentially.
So there are lots of different solutions that are coming out or are out, and they all talk about grid resilience and grid monitoring and so forth and wildfire reduction. How do you find a place in that in a crowded field? Like, where is your lane in kind of all of the solutions that are out there now?
Yeah, I love this question too, because a lot of times that I give talks on wildfire tech or kind of explain the process, I like to divvy it up into three categories. Wildfire really has pre ignition, right? What can we do to understand and fix something before ignition happens? We have post ignition, the fire started, there's smoke in the air. How do we understand the movement, development, location, et cetera? And then we have deployment. Then once we understand that, how do we get out there and put the thing out, right? And so there's a lot of startups, really amazing, talented companies in the post ignition phase, right? Like, how do we find the smoke and understand it? But there's just a few in pre ignition, and that's where we really lie. Pre ignition being, we want to know what type of problem we're looking at, where exactly the problem is, which doesn't currently exist, and how to correctly deploy and move into that pathway of post ignition. And hopefully there will be not be an ignition or just deployment being, let's have the deployment be just a basic infrastructure repair, not an emergency response team. And so to give a little bit more context on that, because I've been kind of speaking on a 100-foot view here, is we are a hardware company. We have software back end, but at the end of the day, we're installing hardware onto the power grid that essentially uses like a proprietary signaling, we'll call it, that can pinpoint the exact location of an anomaly, which is, a conductor breakdown, a vegetation contact, whatever thing that is wrong or not, you know, normal for the grid to be experiencing, and where exactly that is located. That way we can say from the office, from the desktop, from the grid operator, okay, we're looking at X and it's in this area precisely. So we know, is that high fire risk area? Is that a low fire risk area? And we're given all the information we need practically instantly to say, this is the best decision to deploy or to respond to that incident to then prevent a disaster.
So let's talk about that sensor. So first of all, how does it communicate?
Yeah, I mean, so we have multiple are deployed, right? So we have one unit per every mile about of the grid. And so we create a mesh network essentially where they communicate amongst each other. They send it to a backend server, and then we have a grid operator interfacing with our user interface or UI. And so they communicate in a variety of ways depending on where it's installed, satellite, cellular, the basic kind of application. depending on how.
So, can utilities use their existing poles and reclosers, or do they need to upgrade in order to use Grid IQ?
Yeah, great question. So this is a key vocabulary, recloser. And so for those who listen not understand or who don't know what reclosers are, or unfamiliar, that's essentially like the current breaker system for the grid. So similar to the electrical pen you have in your garage, there's little breaker switches. You can think about this at a larger, a little bit more complicated scale for the power grid, but it operates pretty similarly. That's what a recloser is. And so a recloser will exist depending on what state you're in, anywhere from like say a mile to 5 miles ish. It varies, but those systems are what we have to protect the grid currently. So if there is a problem found, those things will shut the power off, and then we can go and look at the line, and we can either get a helicopter in the air to fly it, or we can walk the line to kind of find a problem. So those are on overhead and underground systems. Is very portable, very small, 30-minute install time. So the idea is we don't want to have to do a major retrofit to increase this grid visibility. So we can augment, is like I say, or mount onto just any pre-existing system of overhead or underground system. We're applicable to both.
Yeah, I know bringing a hardware sensor to market, particularly one that is out on a pole and taking all the weather and all the abuse out there, takes a lot of iterations, like engineering over and over again. What I'm curious, what do you wish that you had known back then that you know now about this sensor? Like what was kind of a big gap that you had that you finally solved in bringing this to market?
Yeah, I mean, it's a great question. I think anytime you're dealing with voltages that are higher than residential ones, the complication increases, right? And so the way I first started designing this thing was actually using residential voltage, using small wires, sort of like, as we do with any prototype, you build a model. And then eventually I said, if I'm bootstrapping this company for now, I'm gonna have to build a testing site that mimics it better. So I eventually actually just built a small distribution line in my backyard using, classic 4-acer conductor, which is found in a lot of California distribution areas, and did a overhead pole, dug it, concreted it in, put the cross arms in, put the deaded insulators, strung the whole thing, and then hooked up the system to say, is this going to work in the real world, right? So we need to make sure it operates correctly. And what I was really finding through the whole process was there is a benefit of not ever needing to touch the wire, the conductor, right? And in grid speak, anything transmitting voltage and current above like overhead is called a conductor. It's usually non-insulated, and anything below ground is called a cable. It's usually insulated, or it is always insulated. And so there was the problem of how do we touch this thing or not touch this thing and still get the accuracy that we're really desiring for this system. And so it really was an iterative process of, what grid component do we look at it, and do we try to just augment something already there? Do we just build basic smart systems into, fuses or cutouts, which are in the overhead systems, what they're called, that are some protection mechanisms already built in? Or do we just build an entirely new thing? And I would say that it's been a very iterative process where there hasn't necessarily been a one major moment of like, dang, I wish I knew that before, because every step and every complication, we always learn something new and make it better. Right. And so I think in the past year, we've definitely come to a space where we've developed a really great product that'll work on the voltages that were our target, which is distribution level voltages. We can, like I said, do underground or overhead systems. So overhead being wildfire, of course, but underground will have problems as well in the future that we are experiencing, and having this future proofing of the tech be applicable to multiple scenarios is sort of speaking back to the proactiveness that we need to think about for this.
I'm still thinking about what you said about building this infrastructure in your backyard for testing. I can only imagine like the neighbors kind of peering through the blinds going, what is he doing?
Victor's got to be a little crazy, I think.
So let's talk a little bit about use cases. So I know Grid IQ covers detection, location assessment, and acting on fault events, but give me kind of a few for examples that where a utility that isn't using the system today might benefit in adding it into their infrastructure.
Absolutely. So let's paint a visual here. So imagine you're in a rural, dry area, say near Clayton, California, Walnut Creek, California, something like this. That's very dry, high fire risk, probability of a fire happening within the next 30 years is about 100%, right? And so in order to protect this area, what the utility currently does is when there's a high wind event, and as we know, high winds are high fire risk because there is a spark or an ember, it'll travel faster and move quicker if there is high wind. So a lot of times when there's a high wind event, the utility will shut off the grid. That just says, here's some guaranteed safety, nothing will spark. This is called a PSPS, or public safety power shutoff. So this is obviously an inconvenience for those who are receiving power because now they don't have power during this windy storm. Okay, the reason they do that too is because say they, for example, they left the power grid on and there was a problem and it was a high wind event. Now there was a spark and the recloser, the breaker, may or may not have picked up on that. It depends on, how noticeable that arc is and a variety of characteristics. But sometimes they go unnoticed, which is what we can see in the Eaton fire example, which I'll explain later. So say though it did work, right? Say there was a spark and that recloser shut off. Now everyone's out of power and there's a potential ignition and a problem down the line. We don't know where that is. So the way we currently do that is, okay, we need to get a helicopter in the air quickly, which is very expensive. And if it's high wind, can we even do that? Or do we have to wait? Okay, what's the next option? Let's get a truck out there, a bunch of linemen to go walk the line, try to find the problem. This takes a lot of time. And by the time that they actually get to where the problem has started, if it was an ignition, there's a neighbor already called in a couple hours ago saying, hey, there's smoke over here. We need firefighters. This has completely changed. It's no longer an infrastructure repair. It's now a disaster response. And so what we really focus on is if we have a grid IQ system, say, built in to the same recloser pole, so augment the same pole, and we're monitoring that entire line, right? First of all, we could prevent a need for a PSPS because we have real-time visualization, so we don't have to shut off the power. Awesome. First step. Now, so there was a problem. There was an arcing. Great. We know within 0.5 seconds that there's an issue, and that's communicated directly during the storm to the grid operator, exact latitude and longitude, what type of anomaly we're looking at, so we understand deployment and if it's necessary or if it's a false fault, and we can get out there quickly, right? So before the neighbor's saying, hey, there's smoke coming and there's a fire heading toward my house. So it's really the geolocation and the knowledge that we're providing that just builds a real-time visualization of everything that's going on.
So let's talk about a practical level on this thing. I've heard utilities say over and over again that they want something that's low installation costs, low maintenance burden, that, a lot of these things that have come out are quite complex and you've got to bring in a special team to put them in, or they require a lot of maintenance. Tell me how Grid IQ handles that and what kind of the burden is for installation and maintenance.
Yeah. So one thing that we found is very important during the design of our tech is keeping conversations open with those in the field who are going to be interacting with it. Right. So before all this engineering and no research, whatnot, like I grew up in construction. I grew up doing electrical, C10 contractor, like that whole thing. And so one of the biggest problems that existed in the field of construction is the engineers and the field guys didn't communicate. So there was disconnect and obstacles. So through this whole design process, we've been speaking with distribution engineers, of course. We've been speaking with the linemen who are going to be installing it. We've been speaking with anyone who'd be interacting with the technology to say, what would be a pain in the neck for you about this? And how do we fix that in our design so that way it's easy to deploy and you want to do it? And it's I don't want to say fun, but maybe it is fun to put something on there. It was fun for me when I put it in my backyard. So, but changing that process, because once you have a clear line of sight and clear communication open between the installers, the designers, the engineers, etc., things just run smoother and they can be implemented quicker, and overall it just works as a better system.
So that's the hardware portion. What about the data? I know one of the challenges is, ingesting additional data into an existing control center. How do you guys handle that?
Yeah. So one of the problems of why this hasn't been done yet is because there's a lot of data we need to look through, right? And not only is there a lot of data, but there's small anomalies rather small signature differences in the waveforms that we're picking up from the signaling that we inject. And so communicating or converting that to something that we can actually utilize and understand, there is some back end work that needs to be done, right? And so there's varying, like, what's our pulse frequency we have to inject? Is it higher during a high fire risk? Is it lower during just basic maintenance, right? And then once we have that data, communicating with our backend. So we have a backend algorithm that essentially we built. It's like a machine learning algorithm that shuffles through all this data, of course, and looks through all the different waveforms. And we can find those small changes and understand them based on some backend ledger that we've built. So a lot of our testing has been, how do we simulate particular faults and understand the waveforms that are associated with that so we can be better educated to communicate to the operators.
So would you say grid IQ is kind of a one size fits all? Are you targeting the largest utility? I mean, what's kind of your go to market on that? Because I know sometimes things are a better fit for the largest utilities based on their infrastructure versus, say, a co op or a smaller utility.
Mhm. So our target right now is anything that operates within distribution level voltages. So we say, 1 kV to 60 kV is traditional distribution. Currently, we're working in 1 kV to 38 kV, um, based on the hardware, and that covers most of our target customers. But it really is. It's hard to say if it's a one size fits all because the large utilities, I think, will benefit the most from technology like this because it prevents legal issues, it prevents infrastructure damage. It also provides an opportunity for us to say, look what the utility prevented. Like, here's some awesome PR that you can use to say, now you're the hero. Like, this is great, right? Which I think is very important, is saying, we are doing good work on the grid and let's quantify that and show you. So we actually give reports and like understanding to the grid operators of like, look what could have happened. This is what we've successfully mitigated. So, but that being said, we also work with smaller utilities as well, the small municipals, anything that has that distribution range. And then we expand beyond wildfire too. So like I said earlier, the undergrounding system or undergrounding construction is really what wildfire hardening sort of is the first step. Like, let's just put it underground. And, it's very expensive. There's some whole complications for that, etc. There's also issues with underground systems in terms of the faults and clearing the lines and access and whatnot. So we help with that as well. And we can pinpoint issues. We can keep that healthy. We can clear the line before energization, etc. And then we also have other things. I mean, we have an interesting project right now in Tanzania that we're negotiating and working on, where they have a long rural railway that the conductor goes down, they experience animal contact with the faults, like all sorts of different things interact with the conductor that feeds the train. And it causes an issue where the train will be stalled way out in the backcountry and they need to ship people out there to fix it. This can take a couple days sometimes. So, there's so many different approaches that grid visualization can apply to that wildfire was the ethos point, was the thing I'm passionately connected to, was the thing I felt most related to. But as this company has been growing, I'm realizing there's much more value proposition and application that just helps a multitude of problems.
Sounds like in Tanzania, that might be the beginning of Rail IQ, right? A follow on product?
I mean, maybe, yeah, maybe. I like Grid IQ because I definitely had to work hard not to put anything fire related in the name when I was trademarking Grid IQ and finding the name because I didn't want to just. I had a feeling that there would be some smart system that we'd apply to in the future. I said, how do we open up that door and keep it open where we can tackle the wildfire and really have that as our beachhead market and then be applicable to other solutions that need us.
So we've talked mostly about utilities, and in the last couple minutes, we talked about rail infrastructure. Are there other markets where you see grid IQ being a solution?
Absolutely. So one of the big ones we're looking at right now too is we're currently working on a microgrid up in Northern California. It's in a tribal land reservation, and it's a pretty rural area. And the reason this microgrid exists is because the power grid conductor historically goes down quite a bit there, and they wanted a backup system. This is an underground system, but we're building resiliency in the microgrids with Grid IQ. Meaning, anytime there is a monitoring issue or problem or energization, that line, that web needs to be checked. Essentially, it's called the. Anyway, it needs to be looked at before it's re-energized, right? So we pretty much send our signal through the microgrid. You can think about it like this and see if there is a problem to know if it's safe for re-energization, which then helps any sort of energy resilience or robustness. And so that's really where we come in is how do we rebuild any power grid like resiliency? What is energy resiliency? What is community resiliency? And how do we build a safer system in any of these regards and applications?
So looking ahead 5 years, which is
Yeah.
a long time in this business, I'm curious, how do you see grid intelligence evolving? Like, do you envision a future where mitigation actions, switching decisions, and inspections are increasingly automated?
Man, I mean, the way the world's going right now is I feel like everything is trying to be automated. I think that there will be an application for human interaction, but my hope is that we really gear it toward proactive action, proactive work, as opposed to not knowing something is wrong or outdated or old and then it causing a problem and then saying, okay, look in that direction, let's go fix that thing. But it's hard to say. I mean, energy is an interesting uh, industry where you think it might go in one direction and it ends up going the other direction, right? Like, I mean, at the end of the day, we still have bare wire in the air everywhere we have homes. It's kind of a strange thing to think about. It feels a little bit of an old system, and so I think there will be more automation, more real time visualization needed. But yeah, and of course, I mean, automation I think is a hard to get away from right now.
Sure thing. So, what's your primary focus for, say, the next year? Are you seeking proof of concepts across utilities and other customers? And are you looking primarily kind of at the Western US? Are you looking everywhere? Obviously, you're in Tanzania, so it sounds like international is on the table as well.
Yeah, we in the next year, we're definitely trying to get as many pilots deployed as possible. The more pilots we have, the more ability our system can learn for different scenarios and environments. So that's really our primary focus. We have 3 to 4 pilots planned so far, but we're trying to expand and extend that. One of the ones we're really interested in is Puerto Rico. Not a wildfire area, but high, winds, rain, vegetation contact, and that causes problems in the conductor as well. So that's another pilot we're really wanting to deploy. And then, of course, the wildfire in the western states. We have the railways in Tanzania. We have the microgrids up in Northern California, and then we'll be doing some other, hopefully, wildfire pilots in Arizona, New Mexico, and Catalina Island as well. Yeah.
Aaron, thanks so much for joining me today and sharing the story of Grid IQ. It's really fascinating, and I really enjoyed the whole progression of, I mean, it almost seems like Grid IQ was bound to happen. You had this premeditated idea, and you had to join utilities to figure out how they worked and do all these other things that eventually led to you forming the company and, of course, stringing up lines in your backyard. So, really fascinating story, and thank you so much for joining us today. If you found this conversation valuable, please subscribe, share it with others in the wildfire space. You can find more conversations like this at nealonfire.com and across your favorite podcast platforms. We'll see you next time on Neal on Fire.